Let's get started. So we discussed some housekeeping items. Now let's get to um, what we want to cover for this lecture. So last lecture we looked at BERT and transformer architecture at a high level, but we didn't go into any details. We also looked at a coding exercise. Today's lecture we're going to go into multi-head attention, and we're going to look at the math behind it, and kind of understand it on a more detailed level. And then we're also going to look at SBERT architecture. And if we have time, we'll also look at applications of embeddings to a real world industry application, like namely Instacart. Um, okay, so let's understand BERT and its applications, right? So although I'm saying BERT, this is actually the transformers architecture. So this is not actually BERT. BERT is just this part, right? So this is BERT. The encoding part is used to form BERT, and then the decoding part went into like GPT and other applications, right? So we last time we spoke about position embeddings is a new addition in this transform architecture that can help understand which position a token is or a word is in a sentence, and that can help the model know that, oh, you're in position 5 instead of position 1, and that will help me with the downstream task, maybe classification or whatever is the downstream task. It helps me understand that this is where you're located. So the position embedding takes care of that. So the segment embedding is something that got introduced with BERT, but typically people really care about these two, token embedding, and so practically the token embedding and the position embeddings do matter when we go through transformers. Uh, so in practice, there are like three types of transformer applications. So one is encoder only, which is the left side of this graph, and some applications are BERT, SBERT, sentence BERT, and V transformer as well, where you use like image embeddings. Sorry, you get image embeddings through a BERT-like transformer. So you actually can pass in image chunks as inputs as tokens. So you remember with sentences like words or subwords are tokens. For images, image chunks are tokens. So they're like visual tokens. So the idea behind visual transformer, V transformer, is if you can convert segments of an image as words or visual words, now you can just apply the same transformer architecture on these visual words or visual tokens, and then you'll still be able to do similar tasks. So for images, you would like to get image embeddings, then that's a good application. And so vTransformer did exactly that. So this is a application of encoder only transformer. And this uses only self-attention and feed-forward neural network blocks. So this is like the bread and butter of any most transformer architectures, is having the self-attention component and a feed-forward neural network component. So it's good for classification, summarization, intent detection, image embedding. So still used a lot in industry, right? A lot of use cases in the industry even today. Um, then we have like the encoder decoder transformer, which is like the full transformer that you see in this image. So this is encoder and this is the decoder. So if you use both, that's like the encoder decoder transformer application. So T5, BART are a couple of examples that use encoder decoder attention as well. This is a special attention where you pay attention to the encoder as you do the decoding. So that's why it's called encoder decoder attention. Is you'll keep looking at what happened in the encoder so that you can decode. But this one is not used as much these days at all. Like you don't hear about encoder decoder transformers anymore, because people realize that you can do well with encoder only, and you can also do well with decoder only. So you really don't find applications these days that actually use encoder decoder attention and encoder decoder transformer. So the full transformer, as described, um, isn't used anymore as much. So with decoder only, we see applications like GPT, Llama, DeepSeek. So all the recent innovations are coming from decoder only, because you need to generate, you have to go through decoder. If you just need to discriminate, you can go through encoder. So since everything that we see with large language models is generative in nature, like you generate a sentence, you generate paragraphs. So you have to go through decoder. And it's surprisingly, it is also good for encoder only tasks. So although you're only using decoder, you can also do like classification, summarization, other things that this came up later from from GPT-3 on, people found that it can also do well on encoder only tasks. Um, Yeah. So for that reason, in this course, we'll only focus on either encoder only transformer or decoder only transformer. Like we'll look at BERT and we'll break down multi-head attention and feed forward neural network. So that's the encoder only side. And we'll do the same thing for Llama 3, for example. If you want to understand Llama 2, Llama 3 architecture, that's decoder only. We'll look at that, but we'll not focus on the encoder decoder component, right? Because it's not used as much. So it's not very practical for us. So let's start by looking at encoder only. Um, and then specifically within that, we'll look at this concept of multi-head attention and feed-forward neural network, right? So this is a block that has, uh, let's see, interesting. Okay. Yeah, so this is the block that has like self-attention, and then we also have feed forward neural network. And then we also have layer normalization here, which will also kind of go through. And this is one encoder block. And so if you go back to this, that's basically this whole thing. So we're basically looking at this, but this gets repeated n times. So we'll look at one of these um, transformer blocks, right? So this is like a single transformer, encoder transformer block, right? So that's why it's called encoder number one. So that's the first transformer block, and then you stack many of these blocks. Okay, so within this, we have self-attention and we have feed-forward applied, right? So if you look at self-attention, you see this block goes from left to right, which is like how many tokens you have, let's say X1, X2, X3, X4, so on. They all, like you'll have to interact with all of them, uh, you know, so that's why it's not independent. So you'll have to work with each of the outputs has to depend on all the inputs, right? So this depends on all the inputs and so on. So because of this dependency, the self-attention block is kind of like um, stretches out and it's sequential. Whereas if you look at the feed forward, it applies to one token at a time. So the same feed forward gets applied in parallel. So this is more parallel, you can say, and this is kind of sequential because you have to depend on every token. So that's kind of the high level, right? In terms of how things operate. So the idea is like, let's say you have two words, thinking and machines, right? So my sentence is equal to thinking machines. Then assume that the tokens are thinking and machines. So we've done tokenization and we found thinking and machines. In practice, you might actually find them fall into more than two tokens, right? Because you might break it down into think and then hashtag ing and then whatever. So it depends on how you tokenize. But for now, assume like these are also the tokens. So we have an initial token embedding, right? So this is the token embedding. Now to this we add on the positional embedding. So you remember we had a segment embedding earlier, but we said it's not so important because if for more practical purposes, you can just do with these two. So that's why here we are only looking at these two. So now you add this to the positional embedding, and then you get a new X1, right? That includes the positional embedding and the token embedding. So that's why you see X1 and X1 get replicated here, X2, X2 get replicated here. And once you have this, this is a starting point. Now the self-attention comes into play. So let's look at positional embedding here. So the positional embedding here, so this is going back to this is from the 2017 paper, right? All of this actually is from the 2017 paper, which is attention is all you need. This is like the famous paper that we all should read. If you haven't gone through, you should go through. We're also going through it today in the lecture, but it's a good one to have read start to finish. Um, So this was a paper that kind of transformed the landscape, right? So in there, they say that they use sine of the index times some constant, and then cosine of the index times some constant. So this index can go from 0, 1, 2, so on, right? So as the index changes, the values will change. So you can see that um, the positional embedding, so this is a 256 dimensional embedding, right? 256 dimensions. And then you see there are 20 tokens. Okay, so this graph is actually looking at 20 tokens by 256 dimensions, and then there's one more for the cosine. So it's a total of 512 dimensions. So 256 plus 256. So you can see how do you interpret this graph? Well, the yellow is 1, and then the blue is 0. The dark blue is 0, right? So, and the green is somewhere in between. So you're looking at, if you look at the first embedding, for the first token, it looks like this. It's all green, and then you start introducing some yellow, and then you see it's kind of having this gradient where this yellow is getting pushed out. So the positional embedding would change based on where you stand. So this is just a visual for that. And then this is the cosine, so it's kind of a complement. So that's why you see more of the yellow than the green. But you concatenate the cosine and sine positional embeddings to get the full positional embedding 512 dimensions in this paper. So like you can clearly see the position at 8 has a different positional embedding than say position at 19, right? So when you add this to the same word, same token embedding, you'll have a different final embedding, right? It'll look different. So that's the positional embedding here, um, based on cosine and sine that gets added on to the token embedding, right? So, and then we said, okay, we are looking at one encoder block, but it gets replicated. So you have encoder number 2, then encoder number 3. So the input to an encoder block is, let's say, X1. The output is R1. But this R1 again becomes the input for the next encoder block, and then you get something else, and then keeps going on until you're done. So you can have like many encoder blocks. Like we spoke about this, like if we looked at Llama 3, or yeah, Llama 3 had like 64 of these blocks. But of course, it was not an encoder block, but it's a transformer block in the decoder side. But whatever components Llama 3 would have within that transformer block gets replicated 64 times. You go through it 64 times, X1, R1, so on. You keep going through for each token. So now what we'll do is we'll just look at one encoder block, and within one encoder block, we'll look at one, um, so this is the self-attention is multi-head attention, right? So it has multiple heads, but we look at a single head just to keep it simple. What would happen if you do single head attention on, let's say, two tokens? The two tokens are thinking and machines, right? So let's say the input is thinking and machines. We get this initial embedding. So let's say this is um, token plus positional embedding. So you added them up, right? And then you're calling it x1 and x2. So now what we do is we have these, um, the attention depends on this concept called scaled dot product attention. So it is based on the idea of having query, key, and values. So this is kind of an abstraction, right? Uh, like that's the interesting thing about transformers. There's like abstractions added in there that once you understand, okay, this is it has a purpose, but it's still an abstraction. So, you just have to kind of work through the math, and then you get some intuition about why they might be in place. So the idea here is that the query and the key, they interact with each other across different tokens. And then you get some sense of, for each token, how important are the other tokens to uh, inform what it understands about itself, right? So that's where the attention concept, self-attention comes in, is if you have a sentence, uh, if I want to understand what's the role of this word in the sentence, I need to look at all the other words in that sentence, right? both forward and backwards. So that's the idea of attention, is how much importance do I give to any word in that sentence for this particular word, right? For word I, how important are the other words? So that's self-attention, but that is captured through the query and the key matrices. So here we have this query matrix WQ, we have the key matrix WK. They act on X1 and X2 to give you Q1 and Q2. And then, sorry, let's do this. The query matrix WQ acts on X1 and you get Q1. It acts on X2 and you get Q2, right? So Q1 is X1 WQ and Q2 is X2 WQ, okay? And the same thing goes for K1 and K2. So K1 is X1 WK and K2 is X2 times WK. So it's a vector matrix multiplication. X1 is a vector and W is a matrix. So you're just multiplying a vector with a matrix like we do in linear algebra, and then you get K. So these Ks might have a smaller dimension, right? So Q, this, let's say X1 is 512 dimensions. This might actually be 64 dimensions. And the reason is you're doing multi-head attention. So let's say you have 8 heads, 8 times 64 is 512. So this is like a single head dimension, and this is the number of heads. So multi-head attention, the idea is that you can capture different, you can use different matrices for each head to capture different concepts from these tokens or different understanding, and then you pull it together at the very end. So that's why you have multiple heads. But we are looking at a single head. So for a single head, the dimension is the multi-head dimension divided by the number of heads. So that's 64 in this case, right? So if this is 512, you divide by 8 and you get 64, right? So the query embedding dimension and the key embedding dimension, the value embedding dimension are smaller than the original dimension, right? Okay, so now you have query key and values, right? Because you multiply with the matrices. So these matrices they are learned from data. So the data will tell you what WQ should be, WK should be, WB should be. You just set it up. You set it up in a way and you say, okay, let's go train the model. And then the model will say, okay, this is what WQ should be, this is what WK should be, this is what WB should be. Okay. So now let's go through the math of it. So from X1, we get Q1 because it's X1 times WQ. We get K1, that's X1 times WK, and this is X1 times WB. The same thing for this one, right? So this is X2 times WQ, X2 times WK, X2 times WV. So query, key, and value. Okay. So this is where it gets interesting. So if you look at um, let's actually, okay. So let's actually write it down. So let's say we have thinking, and then you have machines, right? Okay, let's use a different color. Thinking machines. And then I also, again, I have the same replica of this. So thinking, and then I have machines. So let's just write down Q1 here, and then Q2 here. Then let's write down K1 here, and we have K2. Okay, so what we're doing is we are computing the dot product of Q1, and so we're doing a dot between Q1 and K2. And we're also doing a dot between Q1 and K1. And this dot product tells you how important is thinking to thinking and how important is machine to thinking. So dot product is based on similarity, right? We remember cosine similarity is based on dot product, right? So the intuition behind taking dot products is based on cosine similarity as well, because in cosine similarity we scale, but in dot product it's unscaled. You don't scale it by the norm of the vectors. So this Q1 dot K1 is the dot product Q1 dot K2 is dot product. So you're saying the key for the key, the K1 is a key for thinking and K2 is a key for machine. So the keys tell you how important is that word to understand this word in that sentence context, right? So obviously thinking is important for thinking because you're in the same place. So the value will be high. But let's say you had like 10 words here, you'll be able to understand how important is each word for understanding this word in the context of the sentence. So that's how the dot products help you do that. So here we compute Q1 dot K1, let's say we get 112, and then Q1 dot K2 is 96. Okay, and it's scaled. So this is scaled dot product attention, right? So we took a dot product. This is dot product, and this is scale. So the scale dot product comes from this, right? You're scaling it by the square root of the dimension of any of the heads. So this one has a dimension of 64. Same for this. Same for this. So now we divide by square root of 64, which is 8. Yeah, so you scale it by, and the scaling helps with, they found that by doing the scaling, it helps with, uh, getting the softmax scores more easily, and also it helps with learning as well. So there is some magic in here on how did you decide to scale by this number or that number. This is something people have experimented and figured out it works, right? So once we scale it, we get 14 and 12. And then how do you get 0.88 and 0.12 from here and here?
Professor,
Yeah.
one question. This scaling is also helping to avoid like having very small numbers, because if we have a dot product very big number, and then when we scale, we are preventing to have um,
Yeah,
very
that's right.
small values.
Yep. Yep. Right. That's right. So from 14 and 12, how do you get 0.88 and 0.12? If you see, these two numbers add to 1, right? So it's a probability. So obviously it's a softmax computation. So how do you do it? What's the formula here?
What is the question?
So from these two numbers, 14 and 12, how do you arrive at 0.88 and 0.12?
Isn't it like e to the power of 14 over e to the power 14 plus e to the power 12?
Yep, that's right.
And then, yeah.
Yeah, and then this is the other one. So this is e to the power 12 divided by e to the power 14 plus e to the power 12. Yeah. So, and if you actually went ahead and did this computation, maybe on Google, you'll get exactly this number. I mean, may not be exactly the same, but you'll get 0.88 something, you'll get 0.12 something. So we took some arbitrary scores, we scaled it, and then we did a softmax and we got a probability. So 0.88 and 0.12, they add up to 1, right? Now this probability tells you that for the word thinking, thinking is important by the factor of 0.88, but machines is important only by the factor of 0.12. So obviously, thinking is important to understand thinking because the word is thinking. So it's self-referential, right? So this score will obviously be high. But the key thing is, what are the other scores? What are the other words in this sentence? In this sentence, we only have 2 words now, but assume you have 10 words, you'll get 0.88, 0.1, 0.05, 0.03, and so on. And so that'll tell you how important are other words to understand thinking in the context of this sentence, right? So this probability always adds up to 1. So it's an easy way to understand. If you get zero point 0.5, that means it's like, there is a significant importance of that word to understand this particular word, right? And then once you get this number 0.88 and 0.12, they are, you got this by combining Q1 and K1, Q1 and K2. So the query and keys, they combine in a dot product fashion to help you arrive at the probabilities. Now what's left is the value. So the value comes because you scale each value by the weight that you just found out. So let's say V1 is the weight for thinking, and then V2 is the weight for machines. So basically, you would say um, the result for thinking is 0.88 times the value of thinking plus 0.12 times the value of machines, right? So this is 0.88 V1 plus 0.12 V2. And so we'll call this result Z1, let's say. And the same thing you do for Z2. So for machines, let's say you get something else, right? So for machines, let's say we'll call this Q. So you'll look at Q2, right? Q2 dot K1 divide by 8, and then Q2 dot K2 divide by 8. So this, let's say this number here is something like, and then let's say you did softmax, right? So we again applied exponential of this, divide by exponential of that plus that. So let's say you get something like 0.2, 0.8. So then you would say, in this case, Z2 is 0.2 V1 plus 0.8 V2, right? And so what we did is we took X1 and then we went through all of this math and we arrived at Z1. So you transform X1 to Z1 and X2 to Z2, right? So this is going through a single head. Now we've just gone through a single head of self-attention, right? Now what we'll do is actually, you'll get many such Z1s from different heads. So you have 8 different heads. Each of them will give you a Z1. So you concatenate them and then make sure it's the same dimension as X1. Because right now, if you look at it, X1 is in 512 dimensions, but Z1 is in 64 dimensions. So when you go from one transformer block to the other, the dimension of a token should not change. So if you pass an X1 of 512 dimensions, you should get another X1 that's of the same dimension. So in this case, if you concatenate Z1s from 8 different heads, then you will get 64 times 8, which is 512 dimensions. So you get back the original dimension. Yeah.
Professor, and also here we have a single head, but once we have several heads, each of these heads is going to be doing analysis only in one type of relationship, like a syntaxis or context or different kind of relationships between the words.
Yeah, they'll be looking
The
at
purpose of
different,
okay.
yes, yes, yes. So what relationships they capture, only they know. But the training will help them understand how to capture relationships between the different words. So the weight matrices learned will be different. And so the query's key value will be different. And so how much, like you might be looking at different things like, are these, you know, maybe these are all verbs or these are all nouns. That could be one relationship, or these are all semantics in some sense they are similar, or could be some other dimension. So it could capture different dimensions that it thinks it is learning from the data. And so the concatenation represents the cumulative understanding from all these heads put together. So you transform. So if you look at the original X1, it didn't have any understanding of machines or what else is coming in the sentence, right? But once you've gone through one transformer block with multiple heads, now you understand yourself for sure because you have an embedding for yourself, but you also understand yourself in the context of other words. So it's a more holistic understanding that happens once you take a token through a transformer block. Okay. So we looked at how a particular token with positional embedding in it goes through the scale dot product attention using the concept of queries, keys, and values to give you a transformed token of the same dimension uh, once you concatenate with other heads, so that you can keep moving it forward. So you can have as many layers as you want. You can have 64 layers like in Llama 3, but if a token was of size 1000, it'll still stay the same size after those 64 transformations, right? And let's look at, yeah, so let's look at this a little bit more on the concept of attention. So we only looked at two words before, but let's say we have these as like the tokens for a sentence. So you can see the sentence itself is, you can obviously understand what the sentence here is, right? The animal um, didn't cross the street because it was too tired, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's like 11 words. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 tokens for 11 words. Okay. Okay. So now if I want to understand what is the, how is it, the word it in this position of this tokens connected to any of the other ones, and you'll see in this particular layer, let's say this is looking at layer 5, so maybe we are looking at the fifth layer, and then in a particular head, it's placing more attention on the an animal, right? So the it here, if you want to understand it, you by self attention, it is pointing to animal, right? So that's how attention helps, because you can understand a token in the context of other words. It's placing more weight on the word animal. Yeah. Okay. Um, so in some sense, once you look at its the initial embedding for it might be some random embedding. It could be anything. Right? It doesn't have to be animal. It could be anything. But once you go through the transformer, the its embedding would be more reflective of the embedding of an animal. So it will be referring more to the animal embedding. So that's how the embeddings will change as we go from one transformer block to the next. Okay. And then it could also place attention on something else. Like we say, obviously it's a probability, right? This is all probability. So it could also place attention on tired. So um, it's saying animal and tired, both are happening. So you take an average of the two, or take some weighted average of this. And so yeah, that's how it works. And obviously we're taking averages of the V tokens. So the V1, V2 that we computed earlier. So that's also something that came from X1, but it got transformed with the V matrix, right? Okay. So that's self-attention in one head of one transformer encoder block that we just looked at. Okay. So if you put it together in a matrix format, like if this is X1, X2, and then we have um, X1 times WQ is Q1 and X2 times WQ is Q2. So if you represent X1 and X2 as a matrix, then it becomes X, and then WQ is the same. And if you represent Q1, Q2 again as a matrix, you get Q. So that's why you'll see things like Q equals X times WQ, K equals X times WK. But you have to see that the individual keys are here, K1, K2, V1, V2, Q1, Q2. Okay. So this is the matrix representation of the same thing. So um, if we kind of look at it all at once, so our input is thinking machines, right? So this is X1 thinking, and this is X2 machines. We have 8 heads. So you'll have 8 sets of these weight matrices for query, key, and value. So this is W0Q, which is the first head indexed by 0 for query, and then the key and the value. And then W1Q is W1Q, W1K, W1V are this is the second head. So first head, second head, and so on. So you have so many matrices, right? And so each of them will give you a QK, Q0, K0, V0, and so on, Q1, K1, V1, so on. And each of them will give you uh, So this is for thinking, this is for machines, and the same thing, thinking, machines, right? So we'll concatenate all of these, and then this is, I think this is kind of optional, but this is useful in the case where the concatenation of the dimensions don't match the embedding dimension. In that case, this WO matrix will make sure that the resulting dimension here is 512, right?
Like a padding.
Yeah, it's kind of like not just padding, it's transforming because this is again a weight matrix. So it's more than padding. It's transforming it. But yeah, so assume this is not there, assume W0 is not there, then you're just taking all of these thinking ones and then concatenating into a 512 dimension vector. And then you do the same thing for machines, right? So basically you do all of this and you go from X to a new X, let's say we call it R, but you can just still call it X because you're just transforming each token. Okay. Um, the other one I want to talk about is layer normalization. So the other thing that happens with uh, this whole thing is layer normalization, which is you have a skip connection. So this is a skip connection is going from X1, skipping these things, and then you go directly here. So when you skip, you add the result of the transformation back to itself and then normalize. So X is what you passed in here. X1 is what you passed in here. X1, X2, right? This is X1, X2. That's what you passed in here. But what you got as a result was Z1 and Z2, right? From here and here. You add the two and then you normalize. So that's what is layer normalization. And this apparently brings in a lot of stability in the training process of a transformer. It's supposed to help with stabilizing the training. Otherwise, it could not converge or there could be other issues. And also it's been found that this helps with avoiding sensitivity issues to starting point. So the starting point for the training is like randomized, which it is, and some of them are like can throw the model off. The layer normalization kind of takes care of that. Uh, some of the earlier ideas to this goes back to if you look at RNN LSTM, we spoke about this in one of the earlier lectures. LSTM added the cell state, which adds kind of is additive in nature, and it was helping um, the recurrence be more stable. So you see the same thing here that you're adding, it's kind of like a cell state. I would think of it that way. It's making it more stable. So you don't forget what you had before, you just add on to it. That's the idea of layer normalization. If you forget what you have before you did some transformation and then you went off in a different direction, then that could be a problem. So you want to stay with what you learned in the previous transformer block, but you want to add to it. So that's the idea of this layer normalization is you keep adding information rather than just like transforming it significantly and then um, might cause issues later. So this is supposed to help with that. Okay. And then whatever you get after layer normalization, we'll call it the new X1. Sorry, in this case, you call it Z1. And then you pass it through a feed forward neural network. So we'll look at this as well. And then the resulting output is a new X1. So new X1, and then a new X2, new X3, and so on. And all of them have the same dimensions, 512, 512, 512. So this is 512 dimensions, right? Okay. So that was layer normalization, helps with stabilizing the transformer. Uh, what we'll also do now is do a little bit more of a math walkthrough. So you guys are really comfortable with the math of it um, for both attention and also for the feed-forward neural network. Okay. So um, let's look at, so we start with X1, X2, let's say X3 is also there. We first get the query for these things. So this is X1 times WQ, X2 times WQ. x3 times wq, right? And then we have the key, which is x1 wk, x2 wk, x3 wk, and you have the value x1 wv, x2 wv, x3 wv. Okay, so this is, all of these are vector matrix multiply, right? And in this case, because of we're looking at one head, so we take something that's in 512 dimensions and then we transform it to a 64 dimensional vector, right? Okay, so that's query key value. And then we have, so we'll call this, so obviously we call this Q1, and this is K1, and then this is V1, okay? And the same thing for the other ones. So now we do the dot products. So we would do, let's say for Q1, we would do Q1 dot um, K1, Q1 dot K2, Q1 dot K3, and so on, right? And then we normalize. So we would actually normalize by square root of 64, which is 8. So we divide by 8, divide by 8. Okay, so this whole thing can be represented as, this is where the matrix algebra helps, right? Because you would say this is Q1, um, mm, let's see, which is the best way to, uh, so let's look at the dimensions of these matrices, right? So Q is X times WQ. So X is what? X is, let's look at this. X is equal, sorry?
Sorry. No, no.
Okay. So let's say there are T tokens. So what is the dimension of X in this case? The X matrix
T.
T.
by,
Because
so this is,
the
each of these
input,
is the 512 dimension embedding. So it's T by 512, right? Yeah. And then what's the dimension of WQ? See, WQ takes a 512 dimensional vector,
512 by 64.
512 by 64, because it takes a 512 dimensional vector and transforms it to a 64 dimension. So WQ is 512 by 64. So now you see Q is actually, what's the dimension of Q? It's
T by 64.
T by 64. Okay.
Oh,
So
Professor, I have a quick question.
yeah.
Yeah, why is it T by 512 and not like 1 by 512? Maybe I missed that part.
So we are stacking each. So think of each embedding as a row vector here. So you have to assume that there is some, it's either a row or a column. So for example, for thinking, this is a row,
Oh,
right?
here x1 is a vector.
X1 is a vector and it's a row.
Oh, okay. Okay. I got it. Okay.
Yeah. So
Thank you.
X1 is in 512 dimensions. So the number of columns tells you the dimension of X1, which is 512. Okay. So T is the number of tokens. So if you could have, in this case, for example, we looked at four, what, 13 tokens or whatever. So we had that example, right? Yeah, so we have 14 tokens. So T in this case is 14. So it'd be whatever that dimension is that you're looking for the input. So it's T by this, right? Okay, so we got that Q is T by 64. So let's write that down. So Q is T by 64. And then same thing for K, T by 64. And same thing for V, T by 64. So if you want to capture this dot product, right, Q times K1, Q times K2, Q times K3, you can see that you can represent it as, this whole process can be represented as Q, K transpose, right? Mm, because it's telling you what is the dimension of QK transpose? So Q is 1 by 64, K transpose is 64 by T. So the inner dimensions cancel, only the outer dimensions remain, right? So let's look at that. Q is 1 by 64 because it's a row vector. So you say it's a 64 dimensional vector. K transpose is 64 by T. So the inner dimensions you don't care about, you only care about the outer. So Q K transpose is 1 by T. Okay, let's add another page here. Okay, so Q K transpose is 1 by T. So that means it's basically each of these tells you the attention for, so actually this is Q1, let's say Q1. Attention for token 1 from all other tokens. Does it make sense? So it's just one number for each token, and that number tells you the score, like we computed earlier, to 12 or 14 or something, right? So
Including itself, right?
including itself, including itself. Like in this example that we saw earlier, the 112 was from itself, right? 96 was from machines. 112 was the contribution of attention, self-attention to thinking from itself. Okay. So in this case, it would have been a 1 by 2 vector, right? So this 112, 96 is a 1 by 2. T is 2. Okay. So going back here, we get this QK transpose is like Q1 times K transpose is 1 by T, right? Now, if I want to do this for every single, I want to do it for Q2 times K transpose. I want to do it for Q3 times K transpose, right? Each of these tells you what is the contribution of all the tokens to token 1, token 2, token 3, right? So that's the self-attention. Now, how do I stack all of this into a matrix, right? So it turns out you can just stack it this way: Q1, Q2, QT. This becomes a matrix, and then K transpose. Because Q1 K transpose gives you one row vector, Q2 K transpose gives you one row vector, Q2. This is the way we multiply, right? You multiply two matrices, then you take the first row of this matrix, multiply by the whole matrix, you get a row vector. And the same thing for every row. So we can call this the Q matrix. So this is T by 64, and then K transpose is 64 by T. So what is, this is QK transpose. So what is the dimension of QK transpose?
T by T.
T by T. Does that make sense? It's T by T because it's telling you for every token, what is the attention from all the other tokens. So for a given token, you get T attentions. For T tokens, you get T by T times T attentions, right? So this matrix, one second, I'm just going to come back. So QK transpose is T by T because, and this is also called the self-attention matrix. So it captures all the attention. So for each token, what is the attention from all the other tokens? And you do it T times, so you get a T by T matrix. So it makes perfect sense. The dimensions make perfect sense here, right? Now we have to still scale it. So from here let's say we scale it. So we get QK transpose divided by 8. So that's scaled. So this is the scaled dot product attention, right? But before that, we have to also apply the softmax. So softmax of this is the scaled dot product attention weights, right? So now we still need to multiply it by the values because that's when we get. So if you look, then again you go back to this, right? So if I had, uh, sorry, let's look at Q1 K transpose. So this gives me the attention weights for each token. If I were to multiply it by this matrix, V1, V2, so on, Vt, What it's going to do is it's going to take each value multiplied by the attention weight for that token, right? And then sum it up, right? So this is going to be Q1 K transpose, the first element times V1 plus Q1 K transpose, second element times V1 and so on. So you get all the attention weights, but you just have to multiply it by the value vectors and then sum it up. That's the weighted average, right? So this you can represent as Q1 K transpose times V, right? So V is what dimension? T by 64. Okay. So this is T by 64. Okay. If you put it together, let me add another page here. So you get, if for all, this is for, so for query one, you get Q1 K transpose V is the, sorry, for token one, right? So for token one, Q1 K transpose V is the Z1, right? Uh, or actually divide by 8 and softmax. So we didn't apply this. Okay. So this is the transformation of token one based on the attention weights with the scale dot product attention. Right. Now, if I want to do it for every query, I get that the scale dot product attention gives me Q times K transpose divided by 8 times V, and the softmax of that equals Z1, Z2, so on. So this is the transformation that's happening through scale dot product attention, represented concisely through the math of stacking all these vectors into matrices. And so the matrix algebra gives you this very concisely, right? So then we'll call this a Z matrix, let's say. So this is the this is what happens with scaled. This is the concise representation of scale dot product attention. Okay. So this is for one head, and then you have to do it for every head, and then you concatenate and things like that. Okay. So the same thing happens, like the math for the feed forward is even more simple. So this is a math for scale dot product attention, right? Being comfortable with this, concatenating, putting vectors together into a matrix and looking at the dimensions is very important for us to understand when you read papers and you see matrices there. The best way to do it is to break it down into vectors and see for one vector what is the transformation, and then you'll understand the whole matrix of transformations as well.
Professor,
Yeah.
then this C is representing each token and the attention that is this token is paying to all other tokens
Yes.
at the same time.
Yeah. I think pictorially it's easy to understand is if you have Q1, Q2, and so on, QT, and then we replicate it. We have K1, K2, KT. So this, this attention is captured by Q1 K transpose divided by 8 times. So this gives you the softmax of this, gives you these weights. What is the attention of token 1, token 2, token 3, token T on token 1 is captured by this expression. Okay. And then this captures all of it for Q1, for Q2, for all the tokens. Yeah, that's why we said that the self-attention matrix is of dimension T by T, because for each token, you get T attentions. And so for T tokens, you get T by T attentions. Okay. All right. So let's look at the math for feed-forward neural network. So we saw that the individual transformer encoder block has self-attention. So we went through it. So self-attention is expensive in the number of tokens, right? So if the number of tokens increase, you can see why token is a limitation. So suppose I had 100 tokens, then I'm looking at 100 by 100, which is 10,000, right? right? That's the number of computations I need to make in self-attention. Suppose I had 10,000 tokens. How many computations do I need to make in self-attention?
Is it T by T?
Yeah, which is for 10,000 tokens, what is it? That's 100 million. Okay. So when you went from 100 tokens to 10,000 tokens, the computations increased from 10,000 to 100 million. So the number of tokens that you can have in a particular sentence or a paragraph that can be processed by Llama 3 or GPT is limited because of this, increase, quadratic increase in computation. So, so that's why, like, the most of the open models have the context window has limitations. Like Llama 3 says, I cannot take more than 8,000 tokens at once because even with 8,000 tokens, you're still looking at like 64 million computations happening for a single sentence, right? Which is crazy. That number is crazy. So that the self-attention has that limitation is that it's quadratic in nature. And so that also leads to the token limitation, context window limitation that we see with open models. Okay, so we'll go through, I think we'll go through the feed-forward neural network as well, but maybe we'll just take like a 5-minute break. We'll come back at 5:20. We'll go through the feed-forward neural network. Okay, so we were at this point where we finished self-attention and going through the walkthrough for a single head, and we said we can concatenate from different heads, and then that's how an individual token of a set dimension like 512 gets transformed to another embedding of the same dimension. So you always keep getting the same dimensional vector for each token, right? Any questions on this? Okay. So let's go through the feed forward part. So what happens is once you do the self-attention, you get the layer normalization done. So you get like these Z1, Z2, Z3, so on. The next part, which is actually a very important part, is to pass it through a feed-forward neural network. And it involves a ReLU activation. And we spoke about last time as well. If you don't have ReLU activation, if it's a linear activation, then it's really useless. It's like you can add as many transformer blocks as you want, but you're not going to get any benefits. So the feed forward part is really simple. Mathematically, it looks like this. So the feed forward neural network in the encoder transformer block basically looks like this. It's you take an x, let's say, actually let's do it z. So let's say you take a z1 and then you multiply it by w, say feed forward neural network block 1, and then you take the max of 0 and this. So this is the ReLU part, and then you multiply it by a different feed forward neural network layer. So this is the result essentially. So and you get, let's say you get a new x1, right? So so if you want to represent it as a figure, so you get z1, so z2, say z3, and then you pass it through this, and then this is actually a bigger, it takes it to a higher dimension. So this is 512, maybe this is 1048. And then you apply the, so this is WF1, then you apply the ReLU activation, and then you bring it down to the same dimensional space. So it would look like this. So this is WF2, and now this is 512 dimensions. Because this was 512 dimensions. Okay, so this is the architecture. So you get like a trapezium, and then its inversion looks like it's inversion, and in between the two, there's a ReLU. So that's the feed forward neural network part. And I mean, it's like it's a good question. Why would you go from 512 to 1048? These are things people have experimented with, but I would say the main thing is there is a transformation here with the ReLU. That's the key thing. This is like the nonlinear activation piece. That's the main one because you got the self-attention from the attention component, but you didn't, you still want to apply some nonlinear activation that comes in the feed-forward neural network component, right? And then you keep moving forward. So this is basically the math behind, and you do the same thing for token 2 and token 3, right? The same process with the same weights. The weights don't change. So you apply it in parallel to every single token. Okay. So we kind of covered that as well. So with this, we have covered the foundation of multi-head attention with feed-forward neural network within one encoder transformer block, and we looked at all of the math behind it. We also looked at the intuition behind it, right? Feed-forward neural network takes care of the nonlinearity and the real uh, nonlinear transformations help the model learn quite a bit. And the attention takes care of good representation. So each token understands its representation from the context of all other tokens. So where do I stand in relationship to all the other tokens in my sentence? That's what the self-attention takes care of. And then the layer normalization is something to help with the learning. It just helps the training is more smoother. So these are the three things that we covered. So with that, let's do a self-attention exercise. Just take like 5 to 6 minutes to do this. So it's very simple. Let's say you had two vectors, x1 and x2, and then you had the encoder matrices um, WQ, WK, WV. Um, let's see, why do we have four of these? Oh yeah, because this is a four-dimensional vector. Okay, that makes sense. So this is 2 by 4. So x is 2 by 4. WQ is 4 by 3. Okay, so it's kind of projecting to a three-dimensional space. Okay, and same thing with WK. WK is 4 by 3 and WV is 4 by 3. So the question is to compute the softmax similar to what we did with the previous walkthrough, right? And you can use Python matrix multiplication to arrive at the solution. Which token does token 2 place more attention on, and what is attention probably? So that's the question, right? Um, if you, yeah, so just take a crack at it. Softmax is not so important to answer this question. So if you, even if you can just compute the dot product and scale it, that's good enough, right? And it's good to know what the attention score or probability you arrived at as well. So intuitively, you know token 2 is going to place more attention on token 2 for sure, because it's like looking at yourself. But let's get the numbers. Just take like 3 to 4 minutes to work through this exercise. Um, you can, yeah, it's good if you can use some simple Python code to run through this. That would be faster.
Sir, um,
Yeah.
since we can't see the notes from the previous slide on the lecture posted on the website, are you able to display the previous slide and then the question content we can see on the slides that are
Oh,
on
okay.
online?
Let me write
Or
down
if,
the
yeah, okay.
computation, right? So it's essentially the self-attention weights matrix equals what is it? It is Q K transpose divide by square root D okay times the softmax of this. Yeah, this should give you the attention weights. So basically you want to compute this.
Okay, cool.
We don't have to worry about V because you're just asking where is the attention. And once you get this, this is going to be a 2 by 2 matrix, right? You want to look at the second row because the question is on the second token. Okay. So this is what, so if you want to do this, I would just do NumPy in Python to get this computation going. You can even just like open a terminal and plug in the Q and K and use NumPy library to get this computation done. On how this might look like. So hopefully you did something like this is, sorry, so let's move forward. So BERT is like going back to BERT, right? Now that we've looked at, so now we'll not kind of go back to any of the foundations again of attention. We kind of spend enough time on it. So in the future, we'll just kind of refer to encoder architecture, decoder architecture, or llama architecture, and then we'll just kind of speak of it at the high level. So looking at BERT specifically, um, the BERT pre-training has two tasks. One is masked language model, and then the next sentence prediction, right? So masked language model is mask a word in the middle of the sentence and have BERT predict the masked word. And next sentence is predict the next sentence by using both positive and negative labels, right? And both of these are like, you can say supervised or self-supervised tasks because you're kind of using self-supervision from the data to kind of generate the to do the training. And the data set is maybe the Wikipedia and book corpus, and nowadays it's like all over the place. You can use data from anywhere. Um, the loss function for masked language model, it mimics what does it mimic? It mimics cross entropy because we're looking at classification, right? Um, so that's kind of like the setup for BERT, is it uses a masked language model, and then you want to predict the missing token. So you want to base it on a classification loss function like cross entropy. So going from BERT to sentence BERT, which is what we're using in mini project one, it uses a Siamese twins architecture, right? So the Siamese twins is where you kind of replicate the weights between the two towers. So these are the two towers, but they're also Siamese twins in the sense that the weights in this tower is the exact same as the weights in this tower. So you're only learning one set of weights, but when you train, you kind of tie them together. You say it's the same weights here, same weights here. So for the purpose of gradient computation, you say the weights are tied. At inference time, you just pass sentence through one set of weights and then the sentence B through the same set of weights, and then you do cosine similarity. This is something that we've been doing, right? Once you get an embedding. So the sentence BERT is based on this concept of Siamese architecture and tying the weights because you essentially are saying, I want to compare two sentences, but I want them to go through the same transformer architecture. So the architecture is fixed. Once you go through the encoding transformer, you get like some token at the very end. Like if you look at what we were doing with the attention and feed forward, we were going from X1 to X1 to X1 to X1 through all the layers. At the very end, you can just take the first token and say, that's my token that represents all of the tokens in the sentence, all the whole sentence, right? So, or you can also do something called pooling. Pooling is this idea of, I have like 20 tokens for a sentence. What is the final embedding for that sentence? I want to pool the tokens in some way. So you can either take the start of sentence token, it's called the CLS token, and say that represents a sentence, or you can also do a weighted average of these embeddings. So that's the idea of pooling. And then you get a single token embedding in some dimension, right? So sentence BERT takes that and then it does this interesting concatenation and it does a softmax classifier on top of that. So they kind of looked at different combinations. Um, like they've tried CLS, max pooling, mean pooling. So these are different strategies, and they found that mean pooling works really well. But its CLS token is not far behind. So if you were to take the first token of the sentence versus the average token of all this, sorry, average of all the token embeddings, you would not be far off, which is interesting, but it's not surprising because every token captures information about all the other tokens in some sense. And the CLS token does do a good job. So anyway, so this is like how this is from the SBERT paper, and they found that using this kind of a concatenation from the two Siamese twins and then doing a softmax does well for training. So if you're doing fine tuning on your a sentence BERT, they may be a recommendation for a loss function to use in mini project, uh, like the fifth task in part two of the mini project is on fine tuning. So you can carefully look at the loss function you're actually using there. Is it the same as this, or is it something different? And what's working, what's not working, you can kind of look into that as you work on that piece. Yeah. So this is the reason we're also looking at Siamese BERT here is because once you cover transformer as a fundamental building block, you can combine it in different ways. In this specific case for sentence BERT, you're combining it in the form of Siamese twins. You're saying, let's tie the weights together, let's twin it, and then let's pass two sentences through it, and then you can do a softmax classification. So that's an interesting application of taking a transformer, encoding transformer as a building block, and then replicating it and then using it for a specific task like semantic search or sentence similarity. Yeah. Okay. And you can see here in this table on different data sets, the sentence BERT does much better than averaging GLOW embeddings and just averaging BERT embeddings, right? So there is a usefulness to doing it in the form that we're looking at with sentence BERT. It does a much better job on the accuracy numbers as compared to just averaging the words. Even averaging BERT embeddings isn't doing as well as sentence BERT. So that was an interesting discovery that people made is like even if you did BERT, if you didn't fine tune it for a specific task, you might not do as well. So this shows the role of fine tuning is like you might have a foundation model, you might have a llama model, you might have a BERT model, but if you didn't fine tune it for a specific task, as you can see here, it's not as good as like sentence BERT that you see here, right? So the role of fine tuning is very, very important. And that's why you see with all these open models as well, there's a foundation model and then there is one step fine tuning, two-step fine tuning, whatever, how many fine tunings people want to do before it becomes really, really amazing. So like this table kind of highlights the importance of that. Okay, so let's see if we have time. Yeah, let's take a look at this one. One more in-class exercise. Just take a minute to read through this and see what comes up for you. And you can just put your response in chat. So that's feed for neural network is just going to it's like a mini BERT. It just transforms inputs into some format where you can then apply a softmax classifier and then you can do some classification tasks, right? So definitely these are all good, but they're not. Yeah, so you'll have to use a decoding architecture. Basically, it comes down to that. Which of these has a decoding architecture? It's only GPT that has it in these examples. Okay. Because if you want to go from natural language to SQL query, that's a generative task. You want to generate the tokens for SQL query from the natural language. So you'll have to use some decoding transformer. Okay. So one last thing before we close is just a methodology for fine-tuning transformers, right? So this is true even for vision or any other task. Is you first start with a base pre-trained architecture. For example, BERT base uncased is one of them that you'll find on Hugging Face, right? So Hugging Face, you might have already used it. If not, you'll use it in this course. So you just pick one. It's already trained. The weights are there, but it's not fine-tuned. So then uh, you kind of have to say, how do you want to use the output from the pre-training into fine-tuning? Like, for example, you can extract the first token. We saw this for like CLS token. We said this could be a way to get an embedding for a sentence. You can also average embeddings. as a starting point. So this is mean pooling. And then you add fine-tuning layers on top of it with some new data that can help with a specific task. And this is what you're doing with SBERT, right? With part 5, you're actually fine-tuning SBERT. So you're actually improving on top of what's already there for a specific task. And then you set up the optimizer, everything, and then you train, right? This is kind of the typical scenario for fine-tuning. This also holds true for even llama models. Like I have a llama model and I want to do some supervised fine-tuning. I start with a specific llama architecture. And with llama, actually, you might not add new layers. So that's a difference. In llama, you might, so we'll talk about it. I think that falls in a different category. Okay. Yeah. So that's a decoding transformer. So for decoding transformers, you do a different type of fine tuning. For encoding transformers, this is kind of the recipe that you typically add a couple of more layers for a specific task, and then you fine tune, and hopefully you do well, right? So in the case of sentence BERT, for example, uh, for sentence BERT, right? So this piece, this is like pre-trained. It already exists. You start with a pre-trained model. The weights are already there, but you're doing fine tuning here, right? Sometimes you might also fine tune the weights here, but these things are really new. So you'll have to fine tune the pooling and anything else that comes up here. So then the last few layers is what you usually fine tune. Okay, so we are short on time, but we'll continue with more on sentence word embeddings for Instacart recommendations next time as a use case, and then we'll move on to decoding transformer. So GPT and how is it different from an encoding transformer, and hopefully we we kind of have enough context from the uh, components of multi-head attention, self-attention, and feed forward that we already looked at. So we don't have to go through all of that again. So we'll just go through things at a high level. But I think for you to better understand some of the details, I think the conceptual assignment will help you with it. So you can actually look at the questions there to understand some of the concepts here in a more in-depth way. Okay. So we'll stop here. And if you have any questions, um, you can stay back. Otherwise, see you on Wednesday.